Now, as we've been working through doing the discrete probability distributions and working with probability theory, you might be wondering, why are we working with this? How is any of this useful for us in our data application? And part of the answer is that is we use population parameters to make estimates of what values we expect to see occur. So we can then identify unusual values. So if we're using our range rule of thumb, which we've worked with before, we have a maximum usual value that would be, in this case, our mu plus 2 times our standard deviation, and our minimum usual being mu minus 2 times our standard deviation. We could use this to make an estimate of values that lay outside what one would expect to see. So remember, applying our empirical rule, we're going to see that we're going to expect 95% of our values should be falling within these two standard deviation parameters. Okay, so before we move on and looking at an application with science, we need to take a few moments and look at the term deviation. So in statistics, deviation is the amount by which a single measurement differs from a fixed value, usually the mean. However, in general language, a deviation has meaning and tone that's shared with deviant, implying something bad, harmful, and dangerous. Now, this can become a problem when we discuss deviation and it becomes consumed in the general language where it picks up these negative connotations that are not part of statistical language. So, if we're applying the statistical term deviation and we're looking at this image here, it'd be accurate to say, for example, the fish on the left has a scale tone that is greater than 2 standard deviations, darker than the rest of the fish on the right. Okay? Making it unusual. Okay? However, it would be an inaccurate statement to say the fish on the left is not as good as those on the right, or that the fish on the left is better than those on the right. Now, you may see this as very obvious and simplistic. Maybe like, yes, of course, that's very easy to see. However, we need to pay attention. We apply this logic to other areas that may not, the ludicrousness of it may not be quite so obvious to us at first glance. So, when we're looking at deviation and we start having statistics and discrimination, statistics can contribute to discrimination. When these differences that are more than 2 standard deviations from the mean, and we apply these to people, it can begin to contribute to discrimination at the individual level and also at the societal level. So the individual level is our personal interactions with others. At the societal level, at this point, we're referring to what we call systematic discrimination, which is stuff that's built into an actual system. Okay, this is one example of these is IQ scores. IQ scores have a very strong history connected with racism and sexism. They were used to justify treating African Americans, Native Americans, and Hispanics as being less intelligent and therefore not quite as human as people of European descent. Similar with sexism, women were often being presented as not having IQ scores that were as high as men. So these scores, which were different from the mean, okay, and by the way, keep in mind that mean had been calculated based on white men, were then seen as showing that they were less than, not quite equal to. So we need to be careful when we're working with these factors. Now, we're not going to go into this too great a detail in this class. However, if you are interested in any of this and you want to learn some more about it, two great books I recommend are called Even the Rat Was White, which is a historical view of psychology, and specifically looking at IQ scores and how this was part of a system of discrimination and racism in the United States of America into the education program, and The Mismeasurement of Women by Carol Tavis, similarly looking at how sexism and how IQ scores and other factors have contributed to restricting resources and access for women. So what do we do when we think about this? One of the things I like to do when I'm working with information and I'm writing up reports for colleagues and consumers is I find it's much more accurate to speak in terms of differences. I simply don't use the term deviation in my writings at all. I talk about differences. So it's meaningful to talk about differences and to be able to talk about how these differences contribute, but avoiding the use of the word deviation itself. Also, one of the things we need to pay attention to is avoid using one variable as a surrogate for another. Okay, so historically, skin tone, hair texture, gender, many of these have been used as an indicator of a person's IQ and even their very humanity. Okay, and this is really important. When we can begin to say someone's not quite as human as us, it begins to excuse ourselves for our actions in treating them different. Now, this may seem that is antiquated and something that we simply don't do anymore, but I interestingly had just a year and a half ago, a student shared with me a story about how she was working at a grocery store and she wanted to apply for a position in the back doing stock. Stocking was paid more than cashiers. The girls, she's told the manager told her that women were only allowed to work cashiers; they were not allowed to work back in the stock room. And she asked him why, and he's like, well, it's very heavy lifting. Now, she was very much in shape. She'd been in the military. So she's like, well, give me, I can lift whatever weight the rest of these guys are lifting. He's like, no, we don't have women. They don't work for the stock room. And that was simply the answer. So that's an example of where somebody's using gender as an indicator of how much a person can lift. So this is just absolutely sloppy thinking at the highest level. I mean, if you're going to have a criteria for a job such as stocking, an ability to lift a certain amount of weight safely is an excellent criteria, but you should test that amount. You should not use something as a gender as a default mechanism that's somehow going to tap into that. So, although we look at this and it's easy in some ways to look back and say that these things are ludicrous, it's clearly obvious that these using these as markers for IQ or even one's value as a person is something that was part of the past, and we're much more enlightened now. The truth of the matter is, we still interact with it quite a bit. So again, very important as you all go off in your careers and you become leaders in your area as you are training to keep in mind when we're talking about being cautious with language, let's talking about a deviation in statistics and being aware of what it means and what it doesn't mean. And often that term deviation gets to be taken and has a whole lot of other things valued on top of it in terms of the person's value and characteristics and other things like that. So we want to move away from that and begin to be careful when we're talking about something as you go along in your careers. Be careful when you're setting criteria. What are the real criteria you need for a particular job and assessing those actual criteria, not using other characteristics as a secondary indicator. And lastly, of course, when we're talking about mostly we do statistics here, but keeping in touch about research design, we also need to keep in mind that many differences may be real, and thus a single type of assessment may not be equally accurate for everyone. So just because an individual does not perform well in one particular intelligence test does not in fact mean that they do not perform well in other intelligence tests. In fact, Sternberg had 8 different types of intelligence that human beings expressed, whereas the tests that we use for academia are only tapping into 2, maybe 3 of those domains. So we need to be able to realize that people may have very real differences, and that is not a problem. That is actually a strength and a resource to be drawn upon in terms of being able to accurately assess and also help individuals meet their true potential. Okay, so after we've wrapped up our paying attention to terminology, being cautious about misusing the language as we move from statistics back into communicating it with others, let's move back into looking at how we're going to use statistics. So if we're looking at using probability theory, we apply the rare event rule. So if under a given assumption, the probability of a particular observed event is extremely small, then we conclude that that assumption is probably not correct. So here we see our unusually high amount or an unusually low amount is we're looking at something that falls that is equal to or less than the probability of 0.05. Now that 0.05, remember, is not just a magic number we've pulled out of nowhere, but that 0.05 is the 5% that lies outside the 2 standard deviations from the mean. So remember, we just looked at the figure and we talked about how there's the 95% of the values fall within 2 standard deviations from the mean. That remaining 5% is exactly what's represented here with our 0.05. So this is the basis of hypothesis testing, which we'll be looking at in Chapter 8 coming up before the 3rd exam. So 0.05 is going to be a number we're going to be working with a lot, and it's important to understand where it comes from and its usage. So, in a rare event rule, if under a given assumption, the probability of particular observed event is extremely small, then we conclude the assumption is probably not correct. This is an if-then formula of logic. It's one of the most basic formulas of logic, and most importantly, it allows us to falsify something. So we can make a proposition based on a given assumption, and then we can then test it and see, based on collection of evidence, whether or not it supports this. This is critical because falsification is absolutely positively the key for scientific process, and indeed the rare event rule, as we see it here, is the foundation of scientific inquiry itself. So let's take a quick example of this. Before we get into working with numbers and statistics, let's just take a moment to look at some actual application of this. So here we have Semmelweis. Now Semmelweis lived in the 1800s before we were aware of microbes or we had telescopes or any of these other factors. So he's not working with any of the knowledge that we have currently in terms of what causes diseases. What he did observe was that previously healthy women died shortly after delivering a child. So a woman had come in perfectly healthy, delivered a child, and died shortly thereafter. He also noticed that all of these women showed the exact same symptoms. Okay, so since they're showing the exact same symptoms, we have every reason to feel that these might be connected together. This is certainly a good question to be asking. Furthermore, Semmelweis observed that the women had a high rate of death following labor if the delivering physician had recently handled diseased tissue in a lecture. Now, keep in mind, we did not know at that time what transmitted diseases, how they were transmitted, or anything of this nature. So it was not uncommon for a physician to go be giving lectures and handling diseased tissues and showing it to students and helping them learn to be doctors, and then going and delivering children from pregnant women. So there was no reason at that time to think that there was anything that they were communicating that was a problem. So Semmelweis, however, made an assumption. His assumption was he suspected the physicians were somehow transferring the disease to the women when they assisted them in delivering the child. Okay, so this is his assumption. So he required physicians in one hospital to wash their hands before assisting the women in labor. Now, this is an incredibly unpopular thing because the physicians were very insulted that Semmelweis would dare to imply that they were somehow part of these women becoming sick and dying. Keep in mind, these are men that are dedicating their lives to helping and healing, and they were profoundly insulted that he might be implying that they were somehow actually killing people. So, looking at Semmelweis's project that he study that he engaged in, we have his two hypotheses. So the first was the alternative hypothesis, based on his actual assumption. So physicians were transferring the disease to the women. Now the null hypothesis would be the opposite of that. Physicians were not transferring the disease to the women. Okay, now we always test the null in science because anything can happen once. So we're always testing the null. We don't test the alternative hypothesis. So if the number of the women dying of the disease in the hospital where doctors were washing their hands was unusually low, falling into that 0.05 level, then we would reject the null and its associated assumption, which would then support the alternative hypothesis that the physicians were in fact transferring the disease to the women. So what we found was, in fact, that women at the hospitals where the doctors were washing their hands between handling diseased tissue and delivery did die at much lower rates. Therefore, rejected the null and supported his assumption that, in fact, somehow, despite the fact that at that point we were not aware of microbes or any other factors, individuals were, in fact, transferring some component from the diseased tissues to the women when they delivered them for labor, and was part of the foundation of what we all take for granted these days of washing our hands thoroughly.